This question was asked in the GATE Physics paper 2021. This is a MCQ having 2 marks. And the question was asked from the topic electromagnetic theory. The question is, an electromagnetic wave having electric field E vector equals to 8 cos kz minus omega t along y cap direction, and the unit is volt per centimeter, is incident at 90 degree, that is normal incidence, on a square slab from vacuum with refractive index in naught equals to 1 as shown in the figure. So according to this schematic diagram, an electromagnetic wave is incident on the surface 1 of the square slab at 90 degree. The slab is composed of two defined materials with refractive indexes N1 and N2. So in the square slab, two regions, that is green and blue, are divided by this diagonal, and this green region has refractive index N2 equals to 1.1 and this blue region has refractive index 2.2. Assume that the permeability of each medium is the same. After passing through the slab for the first time, the electric field amplitude in volt per centimeter of the electromagnetic wave which emerges from the slab in region 2 is closest to. There are 4 options given. Option A 11 by 1.6, option B 11 by 3.2, option C 11 by 13.8, and the last option, option D, 11 by 25.6. So in this question, to solve this, we have to do, basically we have to find the amplitude of the electric field in region 2 after getting reflected from this diagonal interface. Let us see the solution part now. According to the schematic given in our question, the electric field of the EM wave in region 1 is given by E vector equals to 8 cos kz minus omega t along y cap direction. And the EM wave is propagating along z cap direction in the region 1. Now, some portion of the incident EM wave in region 1 will be transmitted inside the slab and will fall on the diagonal interface separated by these two regions. Two situations may occur in this case. First one is the angle of incidence on this diagonal interface is less than the critical angle for total internal reflection. Then some portion of the incident EM wave will be reflected back in this region, and the remaining portion will be transmitted from this interface in this region. The second possibility is the angle of incidence is greater than the theta c, that is critical angle for total internal reflection. Then total incident wave on this interface will be reflected back in this region towards this region 2. Hence, we'll first check what is the critical angle at the diagonal interface. Now, in case of total internal reflection from an interface, if the EM wave is incident on the interface at an angle equals to the critical angle theta c, then after reflection, the EM wave will travel along this interface. So the reflection angle is 90 degree. To find this critical angle in our case, we'll use Snell's law. Now applying the Snell's law, we'll get sin theta c divided by sin 90 degree equals to N2 by N1, which is basically 1.1 by 2.2. So our theta c, the critical angle for total internal reflection, is sine inverse half, that is 30 degree. And we have seen earlier that angle of incidence at this interface is 45 degree. So in our case, the angle of incidence at diagonal interface is larger than the theta c, which is 30 degree. So for sure, the total internal reflection will take place at the interface. as total internal reflection is taking place at the diagonal interface, then the intensity of the incident EM wave on this interface I1 will be equal to the intensity of the EM wave after getting reflected from the interface, that is I2. So I1 equals to I2, and I0 is the intensity of the EM wave in region 1, which is given by half multiplied with C epsilon naught E naught square, where E naught is given in the question, that is 8 volt per centimeter. Here C is the velocity of light or EM wave in vacuum, epsilon naught is the permittivity in vacuum. Now at interface 1, we will apply the Fresnel equation for transmittance. As the EM wave is propagating along z cap direction and electric field vector is along y cap direction, so it is the EM wave with in plane polarization. Now for in plane polarization, the transmitter's formula is this, which is T1 equals to 4 N1 N0 by N1 plus N0 whole square. Now if we put the value for N0 N1 in this formula, we will get T1 is 55 by 64. So we get the transmittance for the interface of region 1 and this region. So the transmitted light from the region 1 to this region of the slab is given by I1 equals to T1 multiplied with I0, that is 55 by 64 into I0, which is your I2, because our I1 equals to I2 in this region because of total internal reflection. Now we will calculate the transmitter's value for this interface, that is interface 2, and it is given by T2 equals to 4 N1 N0 by N1 plus N0 whole square, which is same as the T1, that is 55 by 64. Now the intensity of the EM wave in region 2, that is given by I3, is basically T2 times your I2. Now T2 is 55 by 64 and I2 we have calculated in the previous slide, that is 55 by 64 I0. So your I3 is 55 by 64 whole square multiplied with I0. Now I3 can be written as half C epsilon naught E03 whole square, while E03 is the amplitude of the electric vector in region 2 and I0 is half C epsilon naught E0 square. So if we just cancel out the half C epsilon naught from both sides, then we have E03 whole square equals to 55 by 64 whole square times E0 square. So E03 is 55 by 64 E0. Now E0 is 8 volt per centimeter as given in the question. Effectively we have E03 in region 2 is 55 by 8. So if we just divide the numerator and denominator by 5, then we will get 11 by 1.6, which is our E03 in region 2. So our option A is correct. According to our solution, after passing through the slab for the first time, the electric field amplitude in volt per centimeter of the electromagnetic wave which emerges from the slab in region 2 is closest to 11 by 1.6, that is option A is the correct answer for our question.